Good morning to all. Today we will start a different topic. So, in the last class we talked about the adder circuit. Okay. Now, we will go for algorithmic perspective for computing addition or performing multiplication. Okay. So, let us start with how we do multiplication in general, that is something we can say ki pen and paper method. Okay. And then we proceed in any some sophisticated algorithm available or not, we will check for computing multiplication in computer system. So, let us say how do you do the multiplication. Okay. So, now book we are following is Stallings. Okay. Let us say we want to first is multiplication between unsigned number, that means two positive number. Okay. So, let us say we want to multiply 11 and 9. Okay. So, 11 can be converted as you know. So, 11 is 1 0 1 1, 9 is 1 0 0 1. Okay. So, we need to multiply using say traditional, we say ki pen and paper method. Okay. So, this is something called multiplicand and this is we say ki multiplier. So, as usual, so 1 we multiply with 1 into 1 1 0 1 0 1 1 1. We know the multiplication, right. 1 into 1 is 1, 0 into 1 is 0, 1 into 0 is again 0, 1 into 1 is 1. Okay. So, similarly, now multiplier bit is 0. So, therefore, 0 0 0. Next we move on the left side and then multiply it 0. So, this will be 0 0 0 0. Next what we do, this is multiplier bit is 1. So, therefore, this will be 1, this will be 1, this will be 0, this will be 1. Now, we add them. So, this is something called partial product, and if you see carefully that partial product, every time we are new partial product we started from the after shifting from the after shifting one bit left side. Okay. So, then we add it. So, this will be 1, this will be 1, this will be 0, this will be 1 1 0, 1 1 0, 1, okay, and 1. Okay. So, this ideally it should be 99. So, we can check it 0 1 2 3 4 5 6, 2 to the power 6 means 64 plus 2 to the power 5, right, 32, how much it is 96, 96 plus 2 plus 1. Okay. So, this is giving 99. So, this is very simple method, but it is for the unsigned number. Okay. So, here observation we can note down, it is we are generating. So, let us say if we summarize it, generate the partial product. So, generate partial product or generate one partial product or say partial product 1 for each digit in the multiplier, for each digit or bit in multiplier. Okay. Then observation, second observation, if the multiplier bit is 1, then simply we are writing the partial product is nothing but the multiplicand. Okay. And if bit is 0, then it is nothing but multiplier bit is 0, then the partial product is 0 only. Okay. So, when the multiplier bit is 0, partial product is 0. So, if the multiplier bit, so bit is 0, then partial product is also 0. If 1, then partial product, maybe we can write PP is nothing but the multiplicand. Okay. And then one interesting thing, each time we started writing the partial product up as if we shifted partial product on the left side with respect to the old partial product. So, initially we had 1 0 1 1, now we have the partial product 0 0 0, but we started writing after shifting the partial product 1 bit, our starting point is here. Okay. So, partial product is shifted left by 1 position with respect to the preceding partial product. So, we can write it here, that is partial product is shifted each time by shifted left each time by 1 bit position, okay, with respect to the preceding, with respect to previous PP partial product, and the results must be within twice n. So, this will be the results. Okay. So, same thing can be done with one simple example. Okay. See, we can write the same thing using flow chart. Let us say here we have a start. Okay. So, then we have C A 0, that is 2 register. I will explain it. M is multiplicand, this is also a register C and D, and then Q is a register, we store multiplier. I think we cannot accommodate here, and count is n bit. Okay, each time what we will see, what is the value of Q0? Q0 is nothing but the multiplier bit. If Q0 is 1, then we need to do some kind of operation. Okay. What is that operation? If this is 1, then we should perform addition. Okay. Because if you see earlier what we are doing. So, here if it is 0 bit only we are pushing 0. Okay. So, no need to do perform. Instead of here in this problem is actually at the end we are adding. So, instead of that what we can do, we can have the running partial product. So, you add it this one with this one. So, first partial product, let us say this is PP 0 and this is PP 1. So, while there will be a new partial product, you add it, that is we say cumulative adding or running partial product. So, therefore, no need to store the each individual partial product, that is the way we will do in using the this algorithm. So, then if Q is 0, then no need to do any addition, but we need to do the operation, that is something called shift. Here shift CAQ, CAQ is 3 registers, and then count. So, count needs to be reduce. Okay. Now, again we check whether count is 0. If it is 0, then we are done. Okay. So, then this is the end and results is available in AQ, means 2 register, results is in this register. If it is not, then again we have to check. Okay. So, here whether q bit is 0 or not. Okay. So, this one will trace with one example, maybe we can use the same example here. Okay. With 4 bit only. Earlier we talk about how many bits, let me check. Oh, this is also 4 bit. So, we can do this one, okay, but you need to remember this algorithm. Okay. So, if I summarize it, so there will be a register C, there will be register A and then multiplicand Q and count. Okay. Actually, background of this algorithm is it is implemented within with a circuit. Okay. So, should I go for showing the circuit, or before that let me explain with one example and then maybe circuit will be better to visualize. Okay. So, let us start with one example. So, what we do it as first is we have to initialize the value C and A 0. Okay. So, that is first step C and A 0. So, please note that C is a register and it is a 1 bit register, C is nothing but the carry, and A is another register and Q is another register. The size of register of A and Q is same, and that is the number of bits in the multiplier and multiplicand. So, we should have the same number of bits. If it is not there, so we have to pad 0 on the on the right side of the number. So, that is C is 0 and say we have the multiplicand, see multiplicand in earlier example, that is earlier example here 11 is 1011. Okay. 1011 and then it is multiplier. Okay. Multiplier is what? So, it is 1001. Okay. So, 1001. Okay. So, first step is C is 0, A is also 0, but we should have a 4 bit. Okay. And what is Q? Q is the multiplier. So, multiplier we have 1001. Okay. And then we should have a count how many bits. So, that is 4 bit. Okay. So, multiplicand is also bit. So, it is written here. Now, what you do it? So, this is first step, that is initial value. Next, what is that? We have to check this is Q 0 bit, this is say we can say this is 0 and then this is 1, 2 and 3. So, Q 0 is 1. So, it is if you go back here, if Q 0 is 1, then what you have to do? You have to add this value. So, Q 0 is 1, then what you have to do? You have to add the value, we have to do C A should be added with multiplicand. So, what is the multiplicand? Multiplicand is 1011, right. So, we have to add 1011. So, if you add it, what will be the result? So, result will be 0 1011. Okay. Okay. Then this will be 1001. Okay. And this is the operation we perform, this will remain same. Now, interesting next is one interesting thing here, then we have to do the shift. Okay. Now, shift should be right. Okay, shift right. Okay, shift right. Now, if you see here example what we are doing. So, this partial product what we are doing? We are shifting on the left side, right. Now, what do you do it? So, with respect to this one, with respect to the old one, if I see this one what we are doing, this is we are shifting on the left side. instead of what we will do it, these partial product will shift on the right side. What I wanted to convey is, so I had the old number 1011, paper and pen and paper method. What we are doing, we started writing from this position, that is 0 0 0 and then 0. Instead of doing so, that is means we are shifting left side. Okay. So, now what you do it, we will shift this value on the right side. Okay. So, therefore, 1 0 1 1. Okay. So, starting point is here, that is we wrote it. What we do it, we shift entire 1 0 1 1 on the right side 1 bit. So, therefore, 1 0 1 1 and then the partial product next stage we will start writing from here 0 0 0 0. So, it is the same thing, there is no difference. Earlier we are respecting this one present P P, that is the partial product we are shifting on the left side, but here that is the previously whatever you computed we shift on the right side and then effect is remain same. So, that is why we do on the shift right. Okay. So, once it is performed, then we shift on the right side including the C A Q, these 3 registers. So, now you shift it right side. So, this 0 will come here, this 1 will come here, this 0 will come here, this 1 will come here and this 1 will come here, this 1 will go here, this 0, this will vanish out. So, this will be 0. Now, you reduce the count at 3. So, this is we write shift right C A Q. Now, counter is 0, no, then again what you have to do, you have to see the Q 0 bit, Q 0 position again. Okay, for understanding we can put 1 here, we earlier put 1 here. So, 0, if it is 0 no need to do any addition, simply we do the shift. If you see the algorithm here, if it is 0 then only shift and reduce the counter. So, that is why we do, we shift, this 0 will come here, this will be automatically, this will, because nothing is there. So, 0. So, this 0 will come here, this will be 1, this will be 1, this 1 will come here, okay, and this 2 1 will come here and 0, okay, and then counter this will be 2. So, again shift C A Q and counter will reduce, okay, minus minus. Okay. So, now again that Q 0 be 0. So, what you have to do, again you shift on the right side. So, this is 0. So, 0, this 0 will come here. So, 0 0 1, this 0 will come here, 0, this one will come here, this one will come here, this one will come here. Okay. So, then this value will be 1. So, shift C A Q and count is reduced. Okay. Now, Q 0 is 1, then simply you have to add this step C A Q equal to A plus M. So, C A Q, so C is A and this is C A, you have to add M, M is nothing but the multiplicand. So, you add 1 0 1 1. So, then what will be the value, 1 1 0 1 1 0 1 1 0. Okay. So, we add it here. So, this value will be 0 1 1 1 and this will remain 1 and we write C A equal to A plus M. Okay. Now, what is next step? You have to shift right. So, shift right means this 0 will come here, this 1 will come here, this 1 will come here, this 0 will come here, this 0, this 0, this 1, this 1, this will go out and then value is 0. So, now you have to check count is 0, yeah, count is 0, then result is available in C A. So, result is nothing but, okay, sorry, result is C not C. So, results is available in what is A Q. So, results is A value and q value. Okay. So, the results will be 0 1 1 0 0 0 1 1. So, earlier what we got value? Yeah, what was the 1 1 triple 0 1 1. Okay. So, 1 1 triple 0 1 1. So, this is nothing but 99. Okay. Now, we will draw the circuit. Okay. So, circuit is something like that. Okay. So, we will have multiplicand, okay. Then we have n bit adder, okay. Then we have say this is shift and add logic control. So, this is shift and add logic control, and then we have what is that CAQ. C is a resistor, A is also a resistor. So, if there is a overflow, it will come to C, okay. And then we have Q here. Obviously, we have starting with Q 0 and obviously Q n minus 1, okay. Okay. So, if you shift it here, so it will come here, okay. So, now how it will work, that I will explain here. So, what we have, if we this will be feed with here, because we need to perform C A to A plus M. So, input will come from here, this is multiplicand, okay. So, addition will be performed. After the addition, results need to be stored into C A. So, therefore, it should come here, okay. And when shift is required, so that will be decided by the Q 0 bit, okay. So, then Q 0 bit, if it is 1, so then shift, not only that, addition operation also will be performed. So, shift will perform, so on 3 register. So, therefore, we can write something like that. So, this is shift right, okay. So, we have the multiplicand. So, if Q 0 is 1, then what we have to do? We have to add what? We have to add A plus M. So, therefore, this A will go here, M will come here. So, after addition, that results will be also stored into C and Q register. So, therefore, C and Q. After that, that shift will perform. So, for shift operation again, so this is the operation on the right side, it will move entirely C A Q, and it will, if it is 0, then there will not be any addition, only shift operation. So, this is the entire circuit for the multiplication of 2 n bit unsigned number. Okay. But problem with this method is that you cannot add the negative number, you cannot multiply the positive negative, that means it will work only for the unsigned number, positive number, but if the number is positive negative, so it will not work. For that, we have to study a different algorithm, okay, that was introduced in 60s, in the last century, is something called Booth's algorithm. Okay. So, in Booth's algorithm, actually it will work for the positive number as well as the negative number. So, that will be discussed in the next class.